Hello everybody, and welcome to the last class of Control Linear System. So in this class we are finally seeing some examples of control design, and we will just basically conclude the topic. So what is control design? The problem of control design, we already talked about it a lot, is that you are given a system, a plant, a device modelized with a transfer function, which means again linear ordinary differential equations. You might have a transfer function that represents a nonlinear system. In this case, the system has been linearized before you could derive the transfer function. Anyway, when we are at the control design time, we assume that we have a transfer function representing our system. What we want to do is to add another transfer function together with the old one. In this case it's called C, with this scheme, which is the so-called feedback loop scheme, with a negative feedback in general, such that we replace the old from U to Y system, the system, let's say, that is not being steered by an automatic control. We replace it with a YREF to Y system. So basically what we want is that Y follows YREF, the reference signal, as best as possible. And usually this as best as possible is quantified in terms of a set of specifications. And this specification, we have seen, they can be translated into frequency domain specification that can be coded into the Bode plot of the loop transfer function, which is in this case C times H. So what is the tuning procedure in this case? First, you draw the Bode plot of H, assuming like C is 1. If C is 1, the Bode plot of H is the Bode plot of the loop transfer function. Then the second step is to have all the specification written in terms of something that you can see in the Bode diagram of the loop transfer function, typically phase margin, gain margin, crossover frequency, state error. All of them can be seen somehow in the loop transfer function Bode diagram. Then you will need to choose the controller type. We have seen a catalog in the last class of possible choices, and the main driver of these choices is whether you need integrators in the loop from steady state error specification. Typically, if you want a zero steady state error with respect to a step of reference, you need at least one integrator in the loop. You have more complex specification in case you want a zero steady state with respect to other inputs or with respect to perturbations or disturbances. But in general, the number of integrators is determined by the steady state specification, and then the rest of the choice will be determined mainly by the number of degrees of freedom that you need. Okay, if you have a P controller, proportional controller, only 1 degree of freedom. So you can basically set only one specification. If you have more specification, well, you need extra degrees of freedom, so you might need a PD or PID. Each term brings another degree of freedom, another parameter that you need to tune. Then, typically, the following step is to choose the crossover angular frequency, which we call omega C. This is a key aspect. The crossover frequency is the angular frequency at which the loop transfer function must have 0 dB gain. It will not be at the beginning like this. Typically, if you just draw the diagram of H, which is the diagram of L in case your C, your control is just 1, the crossover angular frequency will not be the one that you wish, but you have to set the one that you wish. And then basically, once you have decided the angular frequency that you wish, you either can set a phase margin just by computing the argument of your loop transfer function, which is, as I said previously, the argument of H plus the argument of C, both in the crossover frequency. And at this point, if you assume that the gain, as we see here, is 0, then it means that the distance of the phase from minus 180 is your phase margin. Okay, so basically, once you set omega C, the phase at omega C, this term over here, will set your phase margin. Is basically the phase margin minus 180. And then you have to make sure also that the gain is, as we said, 0 dB at the crossover frequencies. Otherwise, the crossover frequency is not the crossover frequency. Let's say, by definition, at the crossover frequency, you will need 0 dB. Another possibility is to set the gain margin, and then you basically do the other way around. You will need to find another frequency. I call it omega x, which is basically the omega at which you hit minus 180. Just by this line over here, and then you have to make sure that the gain, the modulus in dB at this omega x is just minus the gain margin. Gain margin positive means you are stable, so you need to be lower than 0 dB, so that's why you need to minus the gain margin. Then basically this will set you a system of equations. It can be these two over here or these two over here, replacing the value of the modulus and the values of the phase with the values that you have for your specific transfer function and for your specific choice of controller, and both these and these will disappear. You will have some equations in the unknowns of your controller, because h is already known, and by solving this equation typically you will have the parameters that guarantee your tuning. Well, let's see with an example which makes everything clear. So we have this transfer function over here. The specifications are 0 steady state error for a step reference input, phase margin 45 degrees, crossover angular frequency 0.8 radians per second. There are no poles with strictly positive real part. As you can see here, the poles are -1 and -0.5, so the method can be applied. You have also pole in 0, which doesn't bother us, and this pole in 0 is actually an integrator already there, so with respect to the steady state error, you might know that, well, that helps. Okay, I go to the solution straight away. How we do it? Well, we start, as we said, by drawing the Bode diagram of H. In this case, I use the computer to draw it, but you can draw it by using the rules that we've seen in the second class. And again, if you assume that C is 1, then the loop transfer function is just H, and this is its Bode diagram. So we said that we wish to have a crossover frequency of 0.8 radians per second. 0.8 is over here, this dashed line over here, but as you can see, actually we do not hit 0 dB at 0.8, but we hit it somewhere earlier on. Actually, you can look at the diagram and see that we hit it at 0.375 radians per second. And so what we need to do, we need to add some extra term here, so C will not be 1, will be something else, such that the curve here is lifted up a little bit so that we hit 0 dB at the crossover frequency that we wish, 0.8 radian per second. And at the same time, we wish to change the phase at this value, because we want to have 45 degrees of phase margin. But if you look at the phase right now at 0.8, which is the desired crossover frequency again, you see that we have minus 186, which means that if we only fix the gain here, we would be unstable, right? So typically a proportional controller cannot fix this. Proportional controller will only add a scalar gain here, so it means lifting up the curve but not changing the phase. So we could achieve omega C, but with the wrong phase, which gives us an unstable system. Just to be complete in the explanations here, how did I compute these values over here? Well, you can just look at the diagram. This is done by a computer, but you can compute them by hand. And just using this formula over here, basically, if you replace S with your omega, J omega, the omega that you wish, like in this case, you can replace it with the crossover frequency, for example, to compute the phase and modulus at the crossover frequency. You can compute it and check whether you have exactly the same, and this is basically what I've been doing here. So this is your transfer function, and for omega c equals 0.8 radians per second, how do I compute the argument of L? Well, the argument of L, as we said, is the sum of all the argument in the product. So the argument of 0.5 times the argument of 1 over s times the argument 1 over s plus 1 times the argument 1s to s plus 1. They all sum up. And we know also that we have terms at the denominator. These go with a negative sign. So basically the argument of this is the argument of 0.5 minus the argument of s, which is replaced by j omega c, minus the argument of j omega c plus 1 minus the argument of 2j omega c plus 1. Okay, this is the argument of a positive scalar. It is 0, if you remember the drawing we have done in the second class probably. It is located in the basically on the real axis of the complex plane. This is the argument of a purely imaginary number, and if omega c is positive, then this is 90 with a minus sign in front, 90 degrees. Just to be clear, if this is the complex plane, the 0.5 is located here, so 0 degrees, and j omega c is located here, 90 degrees, with a minus sign due to the fact that it is at the denominator. Then this one will be what? Will be omega c is the imaginary part. We have one real part, and one is positive real part, so we can use the arctangent a tan of omega c, basically. Omega c divided by 1 if you want to be precise, but divided by 1 of course doesn't change. And this one again, a tan c, we are in the same situation, a tan of 2 omega c divided by 1. So this is the way how you compute the value we found in the slide. Is minus 180 something if you work out the computation, right? How do I compute the modulus of j at omega c? Well, it's basically the modulus of everything. Just you can replace the values and make a computation. So j omega c plus 1 to j omega c plus 1. And if you want to work out the computation in the complex domain, that's fine, you can just work it out, and then you will have a complex number here with the real imaginary part, or otherwise you can just make the module 1 by 1, so just 0.5 divide the modulus of j omega c, so omega c, times square root of, well, omega c imaginary part plus real part, square, doesn't change anything, again, times this guy over here, 2j omega c square, so 4 omega c square plus 1. There you go. If you work this out, you will find the value of the modulus at omega c right now, which is not 1, which is 1 corresponds to 0 dB in this case. That's why we need to change it. And if you wish, you can compute at which, let's say L j omega, let's say omega, call it omega x or omega y, just for a change, where you have 0 dB right now. And I remember 0 dB is 1. 0 dB means 1, so you can work out the computation as we did over here. You have 0.5, modulus of 0.5, then you would have omega y, square root of omega y square plus 1, square root of 4 omega y square plus 1 again. All of this equal to 1. If you solve for omega y, well, you will find that 0.357, something like that. That we saw beforehand, where we hit 0 dB at this time. And of course this is not easy to solve because it is if you have to square in order to get rid of the equation of the square roots, it becomes a 6th degree equation, not easy to solve in general, but assume we can solve it. That's why sometimes it's easier to just solve it graphically, as we've seen here, right? Very well. So let's continue now. We understand how we can find these numbers from a graph. Of course, reading the graph is easy, or you can always compute them by hand, and that's also useful when you have to solve the equations the other way around, for example, because you have some unknown parameters, as we are going to see shortly. So what is the problem with this controller over here? One doesn't work because the omega c, the crossover frequency, is 0.375, which is not what we want. We want 0.8, and we want 45 degrees of phase margin, so the phase at 0.8 must move from minus 186.6 to, well, 45 degrees higher than minus 180, which means minus 135 degrees. So we have basically two things that we want to change. Let's say two constraints, which which requires a controller with 2 degrees of freedom, as we said already. A proportional cannot do it. Which other would we choose? Well, we choose something that can increase the phase a little bit, move the phase up, because here the phase is too low. So the best choice would be a PD controller. If you remember, the PD controller, its Bode diagram starts, the phase Bode diagram starts flat and then goes up 90 degrees. So that's exactly what we want. Now we consider the PD controller without the pseudo derivative, without the filter, just the pure controller, and then we'll add that thing later if needed. So the first equation we'll set is to set the omega c, the crossover angular frequency, at 0.8 radian per second. So again, what is the angular frequency of this thing over here? Well, it is the angular frequency we computed before. We had it. They sum up, so minus 186 plus the angular frequency of this, which is the angular frequency of a scalar kp 0 plus the angular frequency of the phase of this, which is 0, plus the phase of this one. So if we compute the phase of this term over here, we have this term over here, which is the extra phase that we want. And what extra phase we want? Well, we want to go from minus 186 to minus 135. So we need to increase the phase of 51 degrees. So we want this extra term we add. Remember, the L, the phase of L is the sum of this plus the phase of C. So if the phase of H at the crossover frequency is minus 186, then we need an extra term to bring it to minus 135, and this extra term must be 51.6 degrees, which is the difference between minus 186 and minus 135. So this extra term, the phase of the extra term, must be 51.6 degrees. And the phase of this extra term is the phase of the scalar 0 plus the phase of this one. So real part, imaginary part, imagine replacing S with j omega c, arctangent of tau d times omega c. And this must be equal to this one. So this can be solved. You can just take the tangent both sides. Tangent of this becomes tau d times 0.8. Tangent of this one is the tangent of this one. And then tau d is just this formula over here. Remember, tau d is time, so 0.58 seconds. We already get the first parameter. Second parameter is kp. How we fix kp? Well, in order for omega c to be omega c, we need that the modulus at omega c is 0, right? So in order to have the modulus as omega c 0, we mean that the sum of the two moduli in dB must be 0. So the modulus of this guy plus the modulus of this guy must be 0 at omega c. So mainly if you solve for 0 dB, you get basically that the modulus of c must be the minus the value of the modulus of h, and this in dB. If you pass from decibel to units, let's say, this means that the product of the two must be 1, so the modulus of c at j omega c must be 1 divided by the modulus of h at j omega c, which we have computed just beforehand, right? It was this guy over here, right? This guy over here, this one, right? Now let's go back to the slide. So that's just the computation we done again. So the c at j omega c in dB is minus the modulus in dB of h at j omega c in unit 1 divided by modulus of j omega c. And what is the modulus of h at j omega c? Well, it is this one we found in the blackboard before, just inverse. This inverse 1 divided by this one, and this is equal to the modulus of the controller, which is this one, the modulus of kp times the modulus of 1 plus tau d j omega c, so square root of imaginary part square plus real part square, we get this one. So this equation is easy because everything is known, only thing that is unknown is kp. Then you solve for kp and you get the value of kp, and that's done. So the two parameters have been solved, and then this is the final result put together. So you have the Bode diagrams here, the Bode diagram of h alone, the one we saw before, which has the wrong crossover frequency and the wrong phase margin. In case after correction, after adding this term, the loop transfer function becomes the solid line, which hits 0 dB, exactly where we wanted, 0.8 omega c, and the phase is minus 135 degrees, which yields 45 degrees of phase margin. Same story in the Nichols chart. Take the time to stop the video and look longer if you need. Then, of course, the controller we've seen before is not causal because we have a pure derivator. So as we say, you can just add a denominator under a derivator like this, 1 plus tau fs. How to choose tau f? Well, just a simple rule of thumb. Take something that is way smaller than tau d. So this will create a pole that is located way later than where the effect of your derivator is needed. So in this case you take tau f 100 of tau d, and you see how this changes the loop transfer function. Basically the loop transfer function without this filter is the solid one, and the one with the filter is the dash dot over here. And you see the difference between the two start to be noticeable just long way later than the omega c. So actually what happens after the crossover frequency is not really of our concern. The problem, the stability, performance, everything is set by what happens at omega c, where you have your 0 dB. Then the slope downs, the curve will slope down, and then what happens later doesn't really matter so much. So that's why we don't care so much. Also look here, if the phase goes down a lot after a few decades later than omega c, you see the important thing at omega c this doesn't change a lot. Same speech, same story in the Nichols chart. Right? Let's see another example. Actually, the other example is the same transfer function, and we have the same specifications. We are just asked to do it now with a phase lead controller, which is actually not so different from a PD controller. So the story is the same again. We already have one integrator in the loop, which gives us the zero steady state error with respect to the step input. We have desired omega c at 0.8 and desired phase at omega c again, which needs to be increased by 51.6 degrees as we've seen before. So this can be done by phase lead controller, which you remember maybe can give you an extra phase at the desired point. So basically this is exactly what we need here. We need an extra boost of phase of 51.6 degrees at omega c, this one, omega c 0.8, and we need then to make sure that at omega c at 0.8 radian per second the gain is 0 dB. So this can work out. You remember in the past class there is one slide that shows you the recipe how to tune the phase lead control. So we choose a phase lead controller. It has this formula, two parameters A and KL, and the tau L if you wish, and we see in the recipe actually allows you to find these two parameters just by setting A as a function of this phase gain, if you like, this phase extra phase. So the extra phase is 51.6 degrees. We want it at omega c, so omega c is the omega m with respect to the recipe, so the phase, the frequency, angular frequency at which we want the boost in phase. Then you can use this formula to compute A and this formula to compute tau L. So everything is done, only KL is left. And then to set KL, we have again to set that the overall gain of the loop transfer function, so gain of C plus gain of H in dB is 0. So again, gain of C times gain of H equal 1, which brings to this formula over here, which we can solve again in the same way as before. This is the gain of H to the power minus 1. This is the gain of the phase lead compensator, gain of the scalar part plus square root of imaginary square plus real square, imaginary square plus real square. Everything is known because we already computed A, we already computed tau L, we know omega c because it's one of our specification. This, everything is known, only KL left. Solve for KL and you get the value of 1.36. Final result is this one. This controller is already causal, so we don't have any problems. We just see L, we get now again hits 0 dB exactly where we want and at the phase that we want. Same for the Nichols chart, and you can also see the step response for the different controller. Step response doesn't change a lot, so it means that the controllers are more or less equivalent. There is a little bit of gap between the two, but overall you see the settling time and the behavior, oscillator behavior is more or less the same, and this is due to the fact that the specifications were the same. So the step response, the numbers of oscillations, the oscillatory behavior is ruled by the phase margin. So it's not so many oscillation because the phase margin is good, 45 degrees. Let's say in general 30 degrees is enough, 45 is even better. And then the settling time is ruled by omega c. As we said, omega c, 1 over omega c is roughly in the order of the settling time, from 3 to 6 times settling time. So you see omega c is in the order of well, a few seconds, so in the order of 6 divided by 0.8. Very well.